Hello everyone, here's a video presentation of our study. This study aims to investigate the uplift and damping of a railway catenary span by using a friction-based line checking system. My name is Tengjiao Jiang. I'm a postdoctor at the NTNU. The co-authors are Rønnquist, Yang Song, Gustav Thomas Russell, and Peter Novik. We built a camera system, including 2 air scan cameras, a laptop, a trigger, and a laser rangefinder. And we performed uplift measurement of an existing catenary span on the Oslo airport line in Norway. And there are 2 types of trains running on this line. The maximum train speed is around 210 km per hour. And we can see these red points are measuring points, including dropper clampers, middle span point, and a steady arm. This video shows the uplift measurement by the camera system. We obtain the vibration response of catenary wheels when train pass by. And this video shows the vibration response of a steady arm. And finally, we get 69 train passengers in total from this field test. Then we use a friction-based line checking technique to track wheel displacement. And here is an example to detect wheels from noisy backgrounds. This is the displacement data in time series. We can see the yellow dashed line is detected wheel location, and this red point is a checking point. More introductions about these algorithms could be found in our previous study, and the open source code could be found in this link. Finally, we get uplift data of all measuring points in pixels after processing image sequence of the messenger wheel and contact wheel. Then we use a pinhole camera model to estimate the scale factor. This scale factor can convert the displacement from pixels to physical units, such as millimeters. So we get the displacement and acceleration data of all measuring points. The green area is before pantograph passenger, and the red area is when the pantograph is passing the span, and the blue area is after the pantograph passenger. After statistic analysis, we get the distribution of maximum displacement of all measuring points. The middle point are the mean values, and up and lower caps indicate the standard deviations. And we can find the middle span usually experiences a larger uplift over the whole span, and dropper 6 reaches the minimum uplift. And we use a COV SSI method to detect the modal frequency and the damping ratios. Then we extracted the modal frequency and the damping ratios to estimate the relay damping coefficients, alpha and beta. This is the final result of damping coefficients of all measuring points. This distribution shows the spatial variation in energy dissipation within a span. The polar closed part has a larger mass damping coefficient and energy dissipation than that of a central part. And finally, we get the average damping coefficients over all measuring locations. We recommend using these damping coefficients for numerous simulations in the future, when similar catenary systems are simulated. This is the video presentation for this study. Thank you for your attention.